Hi everyone, I officially open today's Spatial Warsaw Seminar where we host Kevin Credit from Maynooth University in Ireland, who is presenting his joint research with our good fellow Maria Kubara from our faculty, from our Spatial Warsaw team, and also Levi Wolf from University of Bristol. So in the very end, after the presentation, each of you could ask Kevin or Maria also any question you like. So I give the floor to Kevin, and thank you for being our guest today.
Yeah, thanks so much. So, yeah, very excited to talk here. This is some research that I have been doing for some time. I've been interested in spatial causal effects. I was lucky enough to be invited to University of Warsaw in 2023, and to give a short course. So, actually, some of this research comes out of the short course, and also something I was working on at the European Regional Science meetings last year. So we're kind of continuing to build on this idea of basically spatial causal inference using machine learning. So the talk I have here, I'll try and move somewhat quickly through some of the introductory material, but the way I organized it was to start at with some of the basic principles of causal inference, partially so that anyone who's listening to this can be on the same page if you don't necessarily have that strict background in causal analysis, but also because the way that we estimate the potential outcomes model, the basic potential outcomes model, is actually repeated again and again in the more advanced and certainly the machine learning models. So it is important to have a pretty good grasp of how the potential outcomes works and what its assumptions are, also because some of those assumptions are broken inherently by spatial data and by heterogeneous data, which then necessitates the use of spatially explicit methods and heterogeneous treatment effects. So we'll talk a little bit about the basic principles of causal inference and potential outcomes, and then spatial adjustments or adjustments that we need to make for spatial data to estimate causal effects. And then I'll get into these causal machine learning methods, which is what I've been working on, as I said, for a little bit now. And part of this presentation is we'll deal with two. Causal forest is something that I've been using for a little while now. And the T-learner is one of the other kind of very commonly used causal machine learning methods, which I have adapted here a little bit in order to estimate a continuous treatment effect, which is one of the central kind of questions that I'm dealing with in this research, looking at continuous treatment effects, particularly in terms of when when some kind of spatial boundary or spatial investment is the treatment, how do we model treatment effects in relation to proximity to this thing, right? So that's like the overarching question that I'm dealing with, and then I'll apply that specifically in the case of this Bloomingdale Trail in the city of Chicago. It's basically an old freight rail line, an elevated rail line that goes through part of the inner city of Chicago that was then renovated and opened as a pedestrian and cycling trail. And so the kind of idea is to use that as a test case to look at these questions about spatially continuous treatment effects and to see which of these methods performs best, potentially, and then also to get some substantive conclusions about the effect of this trail on construction activity in the neighborhood. Okay, so again, quite a bit, but we'll move somewhat quickly through the introductory stuff. So just to start with, a basic foundation about causal inference, and obviously, in some disciplines, certainly economics and even urban planning now is moving a bit in the causal framework. Some people have a much greater kind of introduction to the ideas of causal inference and others don't. But basically, the fundamental idea of causal inference is that we want to find, and really the fundamental idea of scientific research in general, right, is to find some kind of evidence to support a claim that one thing is causing another. So oftentimes this is what we're interested in all kinds of scientific pursuits. Obviously, uh, it's important that the idea that we're getting the cause of one thing on another is important because for a lot of things, certainly in the social sciences, economics, geography, urban planning, um, oftentimes the data that we're looking at is, at one snapshot in time, we can only observe correlations rather than causations. So I have there are lots of great, graphs that illustrate this point. I have this one, murder rate and number of ice creams sold, and you see a positive correlation here. Um, Now, obviously, hopefully, we don't think that increasing the murder rate is somehow causing more ice creams to be sold, right? But these are the kinds of observational data that we tend to have in the social sciences. Usually, um, we're fundamentally looking at some kind of correlation, and in reality, while correlations can be useful, obviously, they can be useful evidence for trying to argue that one thing causes another. Fundamentally, um, we'd like to go deeper in being able to assess that kind of causal relationship so that we can answer the why question, which again is the fundamental kind of purpose of doing most scientific research. So obviously, a lot of the X, Y relationships that we're interested in are confounded by other variables. And you know, this is certainly true in the social sciences. We have transportation and new business creation I have here. This is like the focus of my PhD research and a lot of my research since then. But in a lot of cases, you could ask the question, right? So we might see a correlation of building some kind of new public transport system and then more new businesses around there. But was it the fact that, the public transportation system was put into certain types of neighborhoods, gentrifying neighborhoods, or higher income or better accessibility to the city center, that then caused both the investment to be chosen to be there and also would have caused more new businesses to locate there regardless of the public transport? Or I have this breastfeeding and IQ one, is a classic one in kind of um the parenting sphere. We across many studies, we see a positive correlation between parents' IQ levels and baby IQ levels and breastfeeding. um but there are certainly a number of confounding factors that could be at work there. People with higher IQs tend to have better education, right? And so could education be the factor that's influencing both of those? So anyway, the purpose of causal inference is to try and isolate those relationships that we're interested in so that we can make a really strong claim and, better policy recommendations about what we should actually do. Um, and Obviously, we can do that through study design and statistical methods. And that's ultimately kind of the purpose of working on these spatial causal machine learning approaches, is hopefully to provide a better causal estimate of the effect of, in this case, some kind of transportation investment on some kind of dependent variable so that we can make better decisions about what we plan in our cities and what we prioritize in policy. Okay. So the kind of fundamental causal inference model, um, or I guess you could call it the basic formulation of the causal estimand, which is the estimate of a causal effect, is called the potential outcomes model. Rubin developed this, although it kind of builds on work from even the 20s, right? So it's something that has been around for quite a while. And this is a table from Rubin in 2005. I think it just summarizes the idea very, very clearly. So basically, you have here all of the observations, all of their covariates, and then the potential outcomes are basically y1 here is what your outcome, what your dependent variable value is when you are treated, and y0 is what your dependent variable value is when you are not treated. Okay, so ideally, to find a causal effect, we would simply compare your outcome when you were treated to your outcome when you weren't treated. And as it says here, comparison, that could be simply subtraction. So basically, you know, uh, whatever your outcome is when you were treated minus whatever your outcome was when you're not treated, and that's the causal impact. Right now, there are a number of assumptions that go into this in order to make that kind of assumption. But even more fundamentally, the problem that we have is, at least in our kind of linear, only living in one dimension of space-time here, is that it's impossible for the same unit to be both treated and untreated, right? So essentially, once you become treated, then it's not possible for you to go back in time and observe what your outcome would be if you were not treated purely, you know. So ideally, we would love to be able to have that kind of pure counterfactual measurement, exactly what your outcome would be, both treated and untreated. Because then, if we had that for every individual, we would already be controlling for all possible confounding effects, because it would be literally the exact same individual observed under two conditions. Right? Unfortunately, that is not possible, which is why it's called the fundamental problem of causal inference. And so most statistical methods of causal inference are basically trying to estimate those effects in some other way. Okay. And one thing that I believe it was Neyman kind of explored in some of this very early work is, so even though we can only observe the outcome for treated and untreated units, never both at the same time. So that's what I've kind of shown in the table here. Like, for any given observation, you can only be treated or untreated. So we only get your individual y0 or y1 value, depending on whether you're treated or untreated. However, if we have a large enough sample of people who are both treated and untreated, we can average the outcome for the treated and subtract the average outcome for the untreated to get an average treatment effect across the data. And Neyman, I believe, was the one who showed that average treatment effect would essentially be the same as averaging the individual level treatment effects if those were possible to obtain. Okay, so that's the basic fundamental potential outcomes model. And again, this comes up again and again in the more complex models. Essentially, what we're doing in all of these models is to find some measure of the outcome under the treatment condition, some measure of the outcome under the control condition, subtracting them to obtain the treatment effect. And just in terms of statistics, if we were to take a data set and subtract these two averages, that is numerically equivalent to running a regression with a treatment dummy. So the average treatment effect would be the coefficient on that treatment dummy as well. So obviously this works explicitly in a regression framework as well. Now, that is great if we only if, and again, this is also in the table, for a set of common units. So that assumption only works if because we're now dealing with different individuals who are control either untreated or treated, right? So averaging the difference there is only going to work if we can assume that those who are treated and untreated are very, very similar. Ideally, they would be exactly the same. And so one of the fundamental assumptions of this potential outcomes model is that the set of observations who are treated and untreated, essentially the treatment and control groups, need to be as similar as possible. this is called the assumption of ignorability. Basically, part of the idea here is that the treatment assignment mechanism can't be related to the potential outcome. Okay, that's one way to think about it. The reason that the name ignorability comes is because basically, if the treatment assignment was random, then we could ignore the assignment mechanism. So that's just where the phrase ignorability comes from. But basically, fundamentally, either we need to construct a randomized experiment where we are randomly selecting similar individuals into treatment and control group, or if that's not possible, which is obviously the case with a lot of social science and economics research, then we need to control for any variables that might be causing both the treatment selection and the outcome. And obviously we call those confounders. So, a lot of the statistical work that we do in causal inference is trying to identify confounders and then control for them to satisfy this assumption of ignorability. Okay. Now, that's kind of the fundamental assumption of causal inference. We have to be trying to make as similar an estimate across the treatment and control groups as is possible. There's another important assumption that gets us to the kind of spatial relevance of what I've been working on, which is called the stable unit treatment value assumption. The idea here is that the potential outcomes, so the outcome for each observation should be unrelated to the treatment status of other units. And another way that's also phrased is that there are not multiple or hidden versions of the treatment. So basically the idea is, if we're going to try and estimate the true treatment effect, then there can't be spillovers in treatment effects between observations. So the fact that I'm treated should not have any impact on your outcomes or whether you are treated. Okay, in order to get an unbiased estimate of the average treatment effect. Unfortunately, as we know with spatial data, basically, because of Tobler's law and the fundamental characteristics of spatial configurations and spatial relationships, that assumption is going to be violated almost every single time, because we know that there are in most kind of spatial domains, there are spatial spillovers. And in most kinds of spatial treatment effects, there is going to be some kind of spillover in treatment effect or in outcome. And I can explain this in more detail in terms of the specific application. But you can imagine, if we're building a new public transport line and we have new stations and we want to look at the effect of those stations on something, the stable unit treatment value assumption would say, if we have a neighborhood around that station, then the treatment of that neighborhood, so building a station there, should not impact the outcome anywhere else. But a public transport line inherently connects different areas of the region, right? So someone gets on the station there and goes somewhere else in the city. So almost fundamentally, by the nature of a transportation system, because it connects places, is almost inherently violating this assumption. And also, we might have people who live a little bit further away from that neighborhood also using that station. So that is also going to impact the treatment there, is going to impact the outcome in control units as well, right? So you can see how very quickly, with a lot of the spatial kinds of treatments that we might be interested in, this gets very messy trying to meet this stable unit treatment value assumption. Okay, so that is basically the fundamental reason that we want to bring spatial model specifications into causal analysis. And the ones that I typically deal with are kind of your standard spatial econometric specifications. So this is just showing how they compare to one another. So the non-spatial specification would just be the outcome in the post-intervention time period, treatment dummy plus your confounders, okay? In the spatial autoregressive model, we add a spatial lag of the dependent variable, which controls for spillover effects in that dependent variable, right? So that hopefully would isolate the impact of the treatment if there are these spatial spillover effects in the outcome. And we have the spatial lag of X model, where we would include, instead of the spatial lag of the dependent variable, spatial lags of both the treatment dummy and the confounders. So obviously the confounders are controlling for spillover effects in the independent variable, which is an example I just kind of gave, essentially, and this is from another paper that I was interested in, looking at the effect of building a new transport line on CO2 emissions. So the biggest reductions in CO2 emissions were places where people were driving a lot, because that's where the CO2 emissions are measured. However, where those people live is further away from the motorway where they tend to be driving, right? So we would be measuring the outcome drop at a different location from where the intervention is actually influencing their travel behavior. So that's one potential reason we would want to have spatial lags of the independent variables. And then obviously the Durbin specification is just all of the spatial lags combined together. Now, the thing that I'm particularly interested in today is the spatial lag of the treatment dummy, because this is basically that very direct violation of the stable unit treatment value assumption. So essentially, we would want to include the spatial lag of the treatment dummy. Oh, that should be a T, not an X. That should be a T. But the reason we would want to include the spatial lag of the treatment dummy is to control for the spillover effects in treatment, right? So whether the fact that a neighboring unit is treated has an effect on my outcome, right? Which was, again, that is the direct statement of the stable unit treatment value assumption. Okay. And this is important in spatial data, again, because many of the kinds of spatial treatments that we're interested in are going to have spillovers, right? And just to talk about this a little bit more directly, obviously when we were describing the potential outcomes model a second ago, we were conceptualizing treatment as a binary feature. So some people are treated, some people are not treated, right? And that makes sense in a lot of contexts. In a medical context, some people get a drug, some people do not get a drug, right? And in that context as well, there's a much lower likelihood of the SUTVA being violated, because the fact that I got a drug is very unlikely to have some kind of effect on your outcome if it's like blood pressure or something, right? However, in the spatial context, uh, that is very different. And the map that I have here, so this is that elevated rail line that we'll be looking at in the application. But here, I mean, we just have the neighborhood block groups colored by distance from that line. But you can imagine that, the question of how do we define who is treated when we're building a new piece of transportation infrastructure, right? Now, typically in research, we tend to draw kind of an arbitrary boundary and say everyone within this boundary is treated, everyone outside of it we consider the control or whatever. But in reality, that's not how these things work, right? The boundary is kind of permeable, and I may be using the transportation infrastructure even though I live further away. In fact, it's probably not this kind of steady distance decay. It's probably related to the other networks that connect to this, right, and other things. But of course, just this inherent fact that there are spillovers in the treatment effect violates the SUTVA. So what we're doing in this paper, and what we're kind of interested in more generally here, is how to define this treatment status in the context of these kind of spatial spillovers, and what it would mean to model this in different ways. Okay, so what we've done here is basically take a couple different possible versions of modeling the spatial treatment effects. And then what we'll do in the paper here is test them against one another to see how the estimates change. But basically we have the binary treatment indicator. That is, in the spatial context, is basically we'll take a buffer around all the in this case entry points onto the pedestrian cycling trail, and we'll say if you're within that buffer you're treated, if you're outside of that buffer you're untreated. A slightly more contextualized version that goes back to this spatial lag of X specification is to say, well, you can have this binary treatment definition, but then we'll also add in the spatial lag of T. So it won't just be whether I was treated, but it will also be the average treatment status of my neighbors. We'll add those two things together to help account for spillovers in treatment. In other words, for a given neighborhood, my treatment effect will be whether I was treated or not, as well as the average treatment status of my neighbors to start to kind of account for those spatial spillovers in treatment in kind of the common spatial econometric way. And then the third version that we're testing is just a continuous value for treatment based on distance decay from the infrastructure, which is essentially just every neighborhood now will get a treatment value on a completely continuous scale based on how far away they are from that one of the entry points. And we're using this distance decay function that I have on the slide here that I've used in other walkability research because it seems to be a pretty good model of actual walking behavior. But obviously we could do a straight line distance. This obviously is a distance decay feature, so it slopes downward at a greater rate than after a certain distance than a simple linear decay. But we could just put in the raw distance, or we could think of some other more complicated kind of version of looking at a continuous treatment effect. Okay. And I guess part of the point here is just that this consideration of spillover effects in treatment hasn't really been dealt with much in the spatial causal literature. And to be fair, spatial causal literature is still relatively nascent, particularly in this idea of kind of adapting the spatial econometric specifications for explicitly causal analysis. Obviously, there's been more work done in difference and differences with spatial adjustments, but it's still a relatively small part of the overall literature. So part of what we're doing here is trying to bring this idea explicitly to the forefront and test the difference in effect that we see between treating treatment in these different ways. Okay. So the other piece of this here that we're connecting, and this has to do more with the machine learning component, is this idea of heterogeneous treatment effects. Okay, and again, just to briefly go back to the fundamental concept here, if we look at the potential outcomes model, as we talked about at the beginning, the fundamental problem of causal inference, I have it highlighted on the table in the box here, is the idea that we can't observe treated and control status outcomes for the same unit, right? So we actually can't observe unit level causal effects directly. However, there are a lot of reasons that we might want to see those unit level treatment effects, because there might be variations in treatment effect across individuals depending on their characteristics. Okay. And, we can think of a lot of different examples of this. Maybe we find that some new drug is more effective in women than in men. Maybe building a new public transport line is more effective in certain types of neighborhoods than in others. Building a motorway may harm certain types of neighborhoods and benefit others, right? So you can think of a ton of different examples of where this kind of treatment effect heterogeneity is actually really, really important for us understanding the fundamental causal effect. And obviously, it'd be important for proper treatment targeting. And even in the kind of urban transportation sphere, we could think of proper planning, right? So that we minimize the harms and maximize the benefits. Obviously, it would help us just understand the explanatory nature of the treatment effect, knowing that some characteristics harm and some benefit, or whatever the case may be. And it's obviously very important for spatial expressions of effects, because if we have the unit level causal effects, we can map them. And then we can look at them and bring in all of our other kind of spatial understandings to those. Okay. And this is a really great diagram, I think, that explains the importance of heterogeneous treatment effects from this Xi et al. Paper. And the quote here, I think, is also very useful. Analysis based on average treatment effect only cannot provide accurate insights when the population is heterogeneous. So what this diagram is showing is basically we have three different types of people. And because we're averaging across their characteristics, we end up with an average treatment effect. But in effect, whatever that size of the effect is, we don't know how much of it is attributed to people who get some benefit from the treatment, people who just don't react to the treatment at all, and people who are actually harmed by the treatment, right? So we get an average number, but we don't know what characteristics are contributing to high or even negative values of that, right? So it would actually be really, really important to understand, obviously, in this case, like if people are being harmed by the treatment, we need to know that. And it could be the case that the people that are harmed are offset by the people who benefit, and we just find a no treatment effect, which is actually, in that case would be unequivocally incorrect, because the treatment is having an effect. It's just going in two opposite directions, right? And that's something we really need to know if we're actually interested in understanding how the treatment works. So the idea of heterogeneous treatment effects, or how it's been implemented, typically is in the regression format to basically create an interaction term between some kind of X characteristic and the treatment dummy. Okay. And we call that the conditional average treatment effect, because it's the average treatment effect conditional on some X characteristic of the observation. Okay. So we can do this in our standard OLS framework. We can create interaction effects with different covariates that we think might be useful to understanding these heterogeneities. And this is done a lot of times in the existing literature, but there are a number of problems with doing it this way. Obviously, there's a limit to how many interaction effects you can run in one model, right? So inherently, our degrees of freedom or multiple comparisons will become an issue if we include too many interactions. So for the most part, we're not going to be able to include every possible covariate interaction with the treatment dummy. So we're going to be missing something there. Obviously, if we're using OLS, there's the assumption of linear fit and linear effects still. And that means that we still tend to not get extremely granular treatment effects anyway. Like obviously the coefficient for the interaction term will give us this conditional average, but it will still be an average effect over that X characteristic. It's still not going to give us the individual treatment effects for every individual observation. So that really is one of the main benefits of using these newer machine learning models for causal inference, because they are able to estimate unit level conditional average treatment effects. And that obviously provides us with a number of benefits for explanatory research and all the things I talked about before. And so the two that I'm using here in this paper are the T-learner and the causal forest. There are a lot of other machine learning models that estimate heterogeneous treatment effects, and this is obviously a very rapidly developing field of study. So I just wanted to explain these models relatively quickly, and honestly, they're somewhat straightforward to understand. And again, the kind of basic inferential framework goes back to the potential outcomes model in a lot of ways. So the T-learner, T comes from two. So it's basically the idea is that we're going to train two models using whatever machine learning algorithm or whatever non-linear machine learning algorithm that we want. They tend to be kind of tree-based models. In this paper, I'm using the XGBoost. But basically, we train two models, and you can see this nice diagram here from this Alves online textbook, which actually, if you are interested in causal machine learning, this is a nice resource for some good code and also explanations of some of these things. But basically, the idea of the T-learner is we're going to train two models on the same data. And basically, we're going to set T equal to 0 in one model and predict our Y values. And then we're going to set T equal to 1 in the other. So we're basically, what we're getting is a prediction of Y, assuming that we're going to get our prediction of Y, assuming that every observation was untreated. And then we're going to get a prediction of Y, assuming that every observation was treated when we drop our observations into the two models. So that's where we get the predictions there. And then we're just going to subtract that predicted value for each individual observation in the treated model minus the untreated model, and that will give us our individual treatment effect for every observation. And then we can average all of those to get an average treatment effect. So we're kind of building, it's a really similar idea to the potential outcomes model, but we're building an average treatment effect up from these individual estimates, okay? Now, the issue with the T-learner is it inherently assumes a binary treatment. And if you remember from what I said before, what we're interested in here is also testing continuous treatments. And the T-learner inherently, like the kind of raw T-learner doesn't do that, because obviously you have to have a model where we are setting T equal to 1 and a model where we're setting T equal to 0. And then we're subtracting those estimates from those two models. So part of what I've done here is to think about how we could use the T-learner framework to estimate continuous treatments. And so basically what I've done here, this graph here is called a dose response curve. So essentially what I've done here is break up all of the values of the continuous treatment. So again, this is that distance decay. In this case, this is that distance decay value. So we have, and this is normalized, but basically we have the very low values on the left of the x-axis, and then the very high values, meaning the higher values here are closer proximity. So basically we're going from being very far away from this pedestrian cycling trail to being very close. And essentially, I'm just running the T-learner for every single one of these. So I think this broke into 1,000 quantiles. And what you see on the dose response graph is basically what is the average treatment effect from each of those runs, given a particular treatment level. So the dose response curve itself can be a useful tool to diagnose causal effects, because you can see here, actually, there's a little bit of odd kind of positive average treatment effects when we're very far away from the treatment, but then for the most part, we just have negative, stable treatment effects for most of the distances until we start to get very close. And then they start to increase quite a bit. Okay, so we can see in the dose response curve, because the treatment is based on proximity, there actually seems to be some relationship with proximity here, which is interesting. But to estimate this continuous T-learner, basically the approach I've taken is to break this into quantiles, run these T-learners, and then basically to choose the value of T that produces the highest average treatment effect, which is the one I've highlighted here. And again, this idea goes back to, I mean, there are different ways that you could maybe analyze this data to try and get at that. But the idea here is, again, we need to create a model where we're considering every observation to be treated. So what does it mean to be treated when it's a continuous treatment? So in this case, we're saying you're treated if you're basically getting a maximum, not the maximum treatment value, but you're getting the treatment value that gives you the maximum average treatment effect. Okay. And then the causal forest, as I mentioned, this is something I've also worked on quite a bit. It's similar to the random forest, but if you're familiar with that method, but instead of when building the tree, instead of making splits that minimize the mean squared error in the dependent variable between the two subsets, it is actually making a split to maximize the difference between outcome for the treated minus outcome for the untreated in each of the two nodes. Okay, so it's essentially building the tree to pick up on treatment effects. And then the test set is dropped into that tree, and the actual estimated treatment effect is essentially a neighborhood weighted average of similar observations in each leaf for the outcome for those who are treated minus the outcome for those who are untreated within each leaf. Now, this is basically because and Athy and Wager talk about this. They're the developers of the causal forest, basically because the random forest and thus the causal forest are essentially a neighborhood weighted kernel estimator in a way. And I have an example if anyone wants to see where I kind of go through a very small example of how this is actually calculated, because I know this could be a little bit confusing if you don't have a prior background in kind of random forest. But basically, you can just understand that essentially each leaf is getting a set of very similar observations, and then we're finding the weighted average outcome for the treated and untreated within each of those leaves, and we're subtracting those two to get the treatment effect within each leaf. And then so if we drop another observation down, it falls somewhere, it falls eventually into a leaf based on its characteristics, and then we predict that its treatment effect will be whatever it is for the leaf that it falls into. We can also estimate continuous treatment effects, or sorry, yeah, treatment effects from continuous treatments in the causal forest. And basically, that is done by estimating an average partial effect within each leaf. So essentially, you get your leaves with similar observations, and then a regression is run of y on t, because we assume that because they're in a similar leaf, those observations are similar. So they should have similar X values. And so we run a regression of T on Y, and that the slope of T in that regression is the average partial effect for a continuous treatment effect. Okay. Anyway, and again, I can talk about this in more detail, but I want to move on to the actual application results. So I mentioned the Bloomingdale Trail. And essentially, in terms of a substantive example, we are interested in generally in trying to assess the impact of non-auto transportation, given all of the negative externalities that go along with auto-dependent transportation systems. And in particular here, we're interested in kind of the economic benefits and development benefits of non-auto infrastructure. I mentioned that this is an area I've been kind of in since my PhD research, so I'm relatively familiar with the literature, but basically, there's a lot of work on the impact of building a new public transport line on new development, property values, new business creation, but there's a lot less for walking and cycling infrastructure. Okay, and so basically what we're looking at in this application is the impact of this walking and cycling infrastructure on construction activity, basically on building permits in adjacent neighborhoods. Okay. So I mentioned a little bit, this is basically on kind of the near west side of Chicago. As I mentioned, there's this disused freight line, and it was converted ultimately in 2015 into a walking and cycling trail. I'll show the pictures, which kind of helps set the context. So it is kind of a very well-designed, cool, architecturally relevant kind of place. It's very well used. And again, it's elevated. So you kind of get this, it's nicely planted and designed. So you get this really sense of separation from the street network, which is really nice. And one of the things I'm showing here, which actually when I was living in Chicago, this is this is like the first impetus for wanting to study this. This picture in the upper right here is actually that mural building there is a coffee shop. And the coffee shop is actually called Ipsento 606. So they're actually using the name of the trail in the name of the coffee shop, which made me think, interesting how important, even kind of psychologically, those business owners felt that this trail was like for the identity of their business, right? So anyway, there's a lot of interest, there is a lot of use. And it is used as a transportation uh route for some people as well, certainly anecdotally. Okay, so basically, I kind of have already mentioned this, but essentially what we're doing here is looking at causal heterogeneous analysis of the effects of opening that trail on building permits, basically at the block group scale. So relatively small spatial units, neighborhoods, or I guess it's smaller than a neighborhood, it's essentially little blocks. And we're going to test the effect of different um, versions of defining the treatment spatially, as I mentioned before. So we used a lot of data. Chicago has a really useful open data portal. So this is where we got the building permit data. But there are also things like crimes, average daily traffic, transit boardings, zoning. So the kind of local regulation. We also have point data on retail locations for different types of businesses, census data, obviously, and then also the street network. So in particular here, we're looking at the building permits, but we're able to use a lot of these variables to control for confounding relationships. Just to show another map here of the kind of binary treatment value. So the green here is the city of Chicago. These are all the block groups. In the purple, these are 4 community areas. So Chicago has very well-defined historical neighborhoods that were actually defined in the kind of Chicago School of Urban Sociology in the 1920s. So there are, I believe, I can't get this wrong, I think there are 77 neighborhood community areas. But anyway, there's a set number that were defined in this sociological study, and they still very accurately kind of represent the neighborhood boundaries in the city. And so for the control area, basically we're looking at the 4 community areas that encircle the 606. And you can see on this map, basically, if we're doing the binary treatment, we essentially just create a 500-meter buffer around the places where you can actually access the trail. And so those block groups that are within the buffer would be the binary treated, and the rest of the block groups within these 4 community areas would be the control. Okay, but obviously we're going to be testing different versions of this continuous treatment. I'm going to move relatively quickly over this so we can get to the results, but I'm happy to talk about essentially what we've done here is create directed acyclic graphs in order to understand the confounding relationships, calculate spatially lagged variables, and then run both the causal forest and the T-learner using 3 different specifications for treatment effect spillovers, and then look at the results. Okay. So just to show you also an example of the DAG that we built. So again, because we have a lot of covariates, we're able to try and include a lot of possible confounders. And so this is just a general example of the one that was built for building permits. So obviously building permits are the outcome, the exposure is the construction of the 606. And we're looking at confounders like education, employment, income, other demographic features, the pre-intervention building permit, number of building permits in each neighborhood, zoning, average age of houses in the neighborhood. Okay, so this is, but again, at least the model specification we chose was actually based on a DAG that we thought, thought hard about and used the literature from. Okay, so these are the primary results. So I guess I spoke for a long time to get to a very simple graph. So what this is showing is basically, so on the left, we have 3 causal forest models, and on the right, we have 3 key learner models, which I'm using XGBoost for. So these are the average treatment effect estimates for each of these models with the standard errors shown. And again, this is the treatment effect on basically building permit density, okay? And the 3 different models are the binary treatment, that's T. T plus WT is the spatial spillover model. So we're essentially taking treatment plus the average treatment value of your neighbors. And then the distance to K is the fully continuous treatment value based on your distance, every block group's distance from one of the access points. And what you can see for both types of models, we have a pretty clear pattern. And this pattern is actually repeated for other dependent variables that we've tested with this in the same application, where if we just look at the kind of arbitrarily defined treatment, binary treatment, we have a somewhat higher estimated treatment effect and also less confidence in that treatment effect. Whereas when we start to include some of the spatial spillovers, we can see that the estimates become more conservative. And I think this is one of the things that we found really interesting when we started doing this, because we would hypothetically expect that if we were just using a binary treatment indicator and violating the SUTVA by not including the spatial spillovers in treatment, then we might be inflating our estimate of the treatment effect, because we're not taking into account those additional spillovers in treatment that might be overlapping. Whereas in these 2 specifications, we are inherently kind of controlling for the spillovers in treatment, and thus we're getting a more conservative estimate. So one of the conclusions and one of the things that we're showing here, now obviously we would need to do a simulated analysis on simulated data to really know this for sure, but it appears that using the continuous treatment indicators produces a more conservative estimate of the treatment effect that is probably more realistic, estimate of the actual effect. And in fact, this continuous T learner value was kind of the lowest out of the set. So that was the one that I went with for the rest of the analysis. So one of the cool things that we can do then, because we're estimating an individual unit level treatment effect for every observation, then we can actually look at how those treatment effects are related to other variables. We can also see how important each of our covariates is in predicting that treatment effect. So what I've done here is basically just build another model where that predicted treatment effect from the T-learner is the dependent variable, and then we include our different covariates, obviously leaving the treatment and Y out. And so if you look at these permutation importances here, we could see that basically the spatial lag of building permits is very important. That makes sense because obviously spatial lag of the dependent variable is likely to be related to places that have experienced more construction activity due to this. But anyway, what's interesting here, actually, if you look at these, you can see, without knowing what these variable names are, you can see that a lot of the top ones are lag, okay? Which is actually a bit odd at first glance, because we're seeing basically here, what this is telling us is that the best predictors of our unit level treatment effects are spatial lags of variables rather than the variables themselves. Seems a bit odd. However, when we start mapping these, I think the actual story of why that is the case starts to come out, and I think it's actually somewhat interesting here. So on the right-hand side, I have just mapped those conditional average treatment effects from the T-learner. So again, these are the unit level treatment effect estimates from the model, okay? And some of them are negative and some of them are positive, so that's why we've used this color scale. And you can see the general pattern here. We have positive effects kind of in the southwest corner, a little bit northwest, and a few over here on the east. And then we actually have some negative effects here in the center. Okay. So what's interesting is if you look at the map on the left, this is just a map of the building permit density variable itself. Okay. And you can see it's almost an inverse pattern here. So the block groups with really high building permit density overall are these ones in the center, kind of along this, northwest, southeast axis here. That's the main road, Milwaukee Avenue. And also along the 606 itself, right? And if you look at where our model is estimating the highest treatment effects, it's a bit of an inverse. It's not a complete inverse. But this is actually really interesting. And it took me a little bit thinking about this, why this might be the case, because basically what this is saying is that the the block groups that were most impacted by the 606 are not those that had the most building permits in total, right? And that's actually the reason why a lot of the most important variables for predicting treatment effect are spatial lags, because you can just see it here in the map. The highest treatment effects are kind of further away from the 606 and from other areas. So that's interesting. And just looking at these maps, you might think like something a little bit weird is going on. But the other cool thing that we can do is just look at the relationships, because our estimated unit level treatment effect basically just becomes another variable. We can just look at how it correlates and relates to all of the other covariates to kind of get an explanatory understanding of the heterogeneity. And so basically what I've done here is map out all the scatter plots between the non-lagged variables and our estimated unit level treatment effects, just so we can try and start to understand what's going on here. And so, okay, we have the building permit lag negative relationship, meaning we have higher treatment effect estimates where we have basically fewer building permits and also the spatial lag of building permits. So we're further away from where there are a lot of building permits in total. Also further away from where there were more building permits in 2010. Further away from block groups with high Asian percentage. But higher treatment effect estimates in block groups with higher levels of unemployment, higher levels of Black population percent, lower median ages, meaning younger, lower education. This is a really interesting one. This is basically higher treatment effect estimates in places where the average time since you last moved is much older. So basically 1980, you see here, there are some block groups where the average year that everyone last moved was 1980. So essentially you have long-standing residents, higher average treatment effect, lower incomes, higher average treatment effect. So in effect, when you kind of look at this constellation of relationships, what we're actually showing here potentially is the 606 is not providing a huge boost to construction activity in places where there's already going to be a lot of construction activity. But apparently, at least from these model results, seem to be showing that it's providing a boost to construction activity in places where we have high unemployment, high Black percent, low median income. In other words, this really kind of gentrification effect potentially, which is actually really interesting to uncover. And, because of the nature of this kind of investment, it's a little bit less for actual commuting, maybe more of, kind of a recreational component, that tie with gentrification might actually make sense. So that's kind of the main substantive impact. So just to summarize on the conclusions, I think went a little long, but tried to move it quickly here. So the overall conclusion, we can look at all of the estimates across 6 different specifications for the most part, consistently positive average treatment effect on building permits from the construction, mostly statistically significant, but relatively small in terms of magnitude. The block groups with the largest treatment effects are, first of all, outside the areas that experience the most overall construction. So it's not the kind of primary driver of most of the building activity. And also tend to be younger, longer duration of residence, lower income education, existing construction activity, again, which might speak to these gentrification effects. And then it appears that using a continuous distance decay specification might provide a more conservative and theoretically accurate estimate of average treatment effects, but obviously we need to do more explicit kind of simulation tests to see if that is the case. Okay, that is it then. So hopefully that was not too much of me just talking for an hour, but thanks.
It was fine. It was an excellent talk. So thank you very much, Kevin, for this really nice and really inspiring